Hello, audience. This is my project, Hacking into the Mainframe Using Math. As a warning, this is a bit rushed last minute. And something else I wanted to say here. That's okay, we're moving on. Towards vulnerability detection for Ethereum smart contracts using graph matching network is the name of the paper that my project is about. In it, the authors train a graph matching network to predict the exploits that have been injected into Solidity smart contracts. The labels that they are testing for in this particular paper are: if the contract has an exploit for reentrancy, timestamp dependency, block info dependency, and TX origin. Oh, the other thing. This is somewhat improvisational. Yeah, slides are missing some information. Here we go. AST is enriched with control and data. So they first make the graph from reading in the smart contracts. It's parsed into this graph representation, the abstract semantic graph. You can see the first little box here. That's the first transformation the data goes through. It goes then through another transformation that enriches it with control and data. Oops, too far. And that transformation, they then feed into, they transform that into an embedding, because the neural networks themselves are not good at handling this sort of, they call it high dimensional data, where it's representing nodes and arrows. Good. Glad I explained that at least. All right. So the AST is enriched with control and data. I said that in the previous slide. This is a more detailed view of what they're doing. You can see this example Solidity contract has been parsed out into abstract syntax tree, and it shows a little bit about what they mean by control and data. The control flow is going to represent where the program execution is, like which step is being taken at any time, while the data flow is going to represent data flow. Oh, dependencies between variables. So where the data is going. And then those two kind of get combined to the abstract semantic graph. And that's supposed to be a good representation of the program as a whole. The control and data flow are two orthogonal representations, so you can't infer the control flow from the data flow, and vice versa. You can't infer the data flow from the control. Oh, yes. That's also the wrong paper. They are citing another amazing paper about graph neural networks that was a bit ambitious to try to recreate. Oh, man. But since this is a two-part submission, I'm not going to do this. Definitely not. All right. Yeah, the original paper, the results that they got were based off of accuracy, recall, and precision in the F1 score. They actually trained two different models. One was to predict the labels from compiled code, and one was to predict the labels from the source code. This first chart here is, or the first section in this chart is going to show what their results are from the, wait, hold on. Oh, I didn't, I didn't capture the whole thing. All right, base G is the byte code. So the second one is the compiled, and the first one is the uncompiled. Let's say source code. Yes. Here's the results. They're comparing the ASG vol detector, their method, with the methods that have come before, and showing that in some cases it's significantly better than other approaches. Yeah, the next slide is a bit, okay, I'll explain myself though, I was trying to make this graph neural network because they're kind of amazing, and they work in a representation of data that's pretty universal, but the math is kind of a lot, and it never actually happened. I did try last minute to create a, what is this called again? LSTM, because the smart contract data has a lot of long range dependencies. It's like code. It's like text data. So I thought an LSTM would be a good format, but it was just, I didn't give myself enough time to do it. It's too fast to change in direction. So there you go. I'm not going to do the next slide. I'll put it on my website. Yeah. All right. Thank you everyone for watching. Bye.